All right, so what if we could just like completely ditch those massive steam turbines that you see in power plants?
Yeah.
I mean, that's a pretty radical idea, right?
It's a pretty wild idea.
That's the whole concept behind direct conversion technology, DCT.
Uh-huh.
And we're diving deep today into this business plan by this fusion scientist, Dr. Lev Nemotin.
Yeah.
And he is laying out how DCT could completely change, like revolutionize how we think about fusion power and other energy sources that just run super hot.
Yeah, I think, I think what's really captivating about this whole concept is the elegance of it. You're talking about harnessing this raw, intense heat from sources like fusion reactions,
right,
and then converting it straight into electricity.
Yeah. No
clunky middlemen, like no moving parts to wear out.
So we're not talking about like some tiny portable fusion reactor here, right? This is like big time power generation.
Exactly. Yeah. This is thinking utility scale.
Right.
Energy production.
Okay. And
Nemotin's plan really focuses in on two promising DCT approaches.
Oh.
One is heat to light, to electricity conversion.
Okay.
Or HLEC. And the other is thermophotovoltaic conversion.
Okay.
Better known as TPV.
TPV.
And both of these approaches aim to kind of shrink down the size of power plants, boost their efficiency, and dare I say, make energy production a bit more sophisticated.
Okay.
A little more elegant.
I am all for a little sophistication in our power plants.
Yeah.
But seriously, why is DCT such a big deal compared to what we have now?
Well, think about a typical power plant today.
Okay.
You burn fuel, you heat water, you create steam, spin turbines, and finally you generate electricity, right?
Right.
It's this multi-step process where at every stage you're losing energy.
Okay, yeah.
So DCT cuts through all of that. By directly converting heat to electricity, you eliminate these inefficient mechanical systems, these systems that require constant maintenance. You get rid of all that.
Got it. So it's like smaller plants, less downtime, more power output for the same amount of fuel.
Yeah.
That's a pretty convincing argument.
Yeah.
And Nemotin's plan specifically highlights how well DCT could work with fusion power.
Right.
Now, why fusion?
Well, because fusion reactions, we're talking, they create mind-boggling temperatures.
Right.
Millions of degrees Celsius.
Wow.
This is a gold mine for DCT.
Okay, now we're talking.
Yeah.
So tell me about this HLEC thing.
Okay.
It sounds like a little something out of Star Wars.
Yeah. So picture this.
Yeah.
You have these special ceramic materials.
Okay.
They're infused with rare earth elements, and they're glowing white hot.
Wow.
Over 2,000 degrees Celsius.
Yeah.
And they're emitting light, but it's not just any light.
Right.
It's very specific wavelengths of light. And these are perfectly tuned for specialized photovoltaic cells.
Really?
It's a high-tech light show that also happens to generate power.
Wait, so it's like a light show that makes electricity?
Exactly.
But how do you keep all of that light focused on those PD cells?
Right.
Wouldn't some of it like scatter and get lost?
Right. And that's where photonic crystals come in.
Okay.
They act like these tiny little traffic cops for light, know? They're guiding those energy-rich photons directly onto the PV cells.
So they're not your typical rooftop solar panels?
No.
These are
multi-junction cells.
Okay.
They can capture a much wider range of the light spectrum. So you're squeezing out every little bit of energy.
So it's all about maximizing efficiency.
Exactly.
Like making sure every little bit of heat gets transformed into usable electricity.
Mm-hmm.
But hold on, if we're like creating this mini sun
inside
of a reactor,
right,
wouldn't the PV cells get fried?
Oh, well, yeah.
By the intensity of the light and the heat?
Right.
Yeah.
And that's where the engineering gets even more impressive.
Okay.
These systems are designed to handle those extreme conditions using clever cooling mechanisms and radiation shielding.
Wow.
To protect those delicate PV cells.
Now that's what I call like hardcore engineering.
Uh-huh.
All right, so that's the light show approach.
Right.
What about this TPV technology? How does that stack up?
Well, TPV is more like a super efficient heat sponge.
Okay.
It uses specialized semiconductor cells. They're made from exotic materials.
Okay.
That are specifically designed to like gobble up heat and spit out electrons.
So instead of sunlight, they're soaking up that heat from those crazy hot fusion reactions.
Exactly.
Wow.
You're talking temperatures reaching 2,500 degrees Celsius.
Wow.
Or even higher.
Yeah.
And to make sure that those PV cells are capturing the maximum amount of energy.
Yeah.
You guessed it.
Photonic crystals.
Photonic crystals.
They're everywhere. What's their role in TPV?
Well, in this case, they act like tiny lasers, emitting very specific wavelengths of light.
Yeah.
And they're perfectly matched to the TPV cell.
So like a very highly targeted energy beam, right?
Yeah.
So you're ensuring that the PV cells are constantly being fed like a maximum dose of energy.
Yeah, exactly.
So both HLEC and TPV are all about precision and control, like making sure every photon hits its target and gets converted into electricity.
Precisely.
And like HLEC, TPV systems can also utilize things like tandem cells to capture multiple bands of light. Yeah. So theoretically, efficiencies could reach like close to 60%. That's wild.
Yeah.
That's practically defying the limits of thermodynamics.
Practically.
But isn't that kind of pushing the boundaries of like what's physically possible?
Yeah.
What are some of the potential downsides or challenges there?
Well, yeah, I mean that's a great question.
Yeah.
And while the theoretical potential is there, there are still, significant engineering hurdles to overcome.
Yeah. All right.
I know.
Color me intrigued, but before we kind of get into those challenges, I have to ask, like, why is Nemoten so focused on fusion?
Right.
Like, why not concentrate on, say, concentrated solar power?
Yeah.
It's already pretty good at, at generating high temperatures, right?
It boils down to the sheer intensity of the heat coming from fusion reactions.
Okay.
We're talking about temperatures millions of times hotter than concentrated solar power.
Wow.
And that kind of heat, that's where DCT truly shines.
So fusion is like the ultimate proving ground for DCT, right?
Exactly.
If it can handle the heat of a fusion reactor, it can pretty much handle anything.
Yeah.
But how would you even integrate DCT into a fusion reactor?
Right.
Like, wouldn't those extreme temperatures and radiation just fry everything?
Right. And that's where Nemoten's plan, I think, gets even more ambitious.
Okay.
He's not talking about, like, tacking DCT on, to an existing fusion reactor as an afterthought.
Right.
He envisions integrating it directly into the reactor itself.
Like right from the start.
Right from the get-go, yeah.
So the DCT components would be right there in the thick of it.
Yeah.
Like bathing in the energy of the fusion reaction.
Exactly. And that means you're maximizing efficiency from the moment fusion energy is released.
Okay.
This approach could potentially make fusion power commercially viable much sooner than anyone anticipated.
Okay, that's a bold claim.
Yeah.
But let's face it, this all sounds incredibly complex.
Yeah.
What are some of the biggest hurdles they need to overcome to make this a reality?
Oh, well, I think you're hitting the nail on the head. This is cutting edge stuff.
Right.
And there are, some major challenges.
Yeah.
First and foremost, we need materials that can withstand, 2,500 degrees Celsius heat.
Wow.
We're talking super ceramics, metamaterials, nano-engineered composites.
So like Captain America's shield, but for power plants.
Pretty much, yeah.
Right.
But it's not just the heat, right?
Right.
Fusion reactions also release a ton of radiation.
Oh, all right.
Particularly neutrons.
Yeah.
And these can cause materials to degrade and become brittle over time.
So we need materials that are both heat resistant and radiation hardened.
And radiation hardened.
That's a tall order.
It is.
But I gotta ask, are scientists even close to like developing something like that?
They're getting there.
Okay.
Scientists are already exploring materials with self-healing properties.
Like self-healing materials.
Yeah.
That sounds like something straight out of science fiction.
It's pretty wild. How does it even work?
It's like having these tiny little repair crews.
Wow.
Working inside the materials, constantly patching up any damage.
Okay.
But, the challenge is they go beyond just materials.
Right.
We also need to rethink how we design the fusion reactors themselves.
Okay, now we're getting into like the really futuristic stuff. Yeah. So what kind of crazy reactor designs are we talking about here?
Well, imagine this.
Okay.
A gaseous blanket surrounding the fusion reaction.
Wait, a gaseous blanket.
Yeah.
Okay.
And it's absorbing that intense heat.
Okay.
While allowing specific infrared wavelengths to pass through.
So that sounds like something out of Star Trek.
Yeah.
How does that even work? And how do you generate light inside this gaseous blanket?
Well, Nemotin talks about a process called three-dimensional volumetric light emission.
It's like a miniature light show happening inside the reactor with carefully chosen gases or nanoparticles emitting light in all directions.
Wow.
And the result.
Yeah.
Everything is bathed in these energy-rich photons ready to be captured.
Okay, so we've got a light show.
Yeah.
Inside a reactor wrapped in a gaseous blanket.
Yeah.
This is getting more and more complex.
Yeah.
We need brand new materials.
Uh-huh.
We need a complete redesign of fusion reactors.
Right.
And on top of that, we need this 3D light show.
Uh-huh.
Who's going to tackle all this?
Right.
Are we talking about like some lone genius in their garage, or are we talking like a massive international collaboration?
Well, Nemotin actually envisions a joint effort between top researchers in the U.S. and Israel.
Well, that makes a lot of sense.
Yeah.
You got the U.S. with its expertise in fusion research, and then you got Israel, which is like a powerhouse in material science and optical engineering.
Yeah.
It's like assembling a dream team for this challenge.
Exactly. He specifically mentions Technion, which is it's kind of Israel's equivalent of MIT.
Oh, wow.
As a key partner in this. So imagine like the best minds from both countries joining forces to solve this.
All right. So we've got the dream team.
Yeah.
We've got like the blueprints and a plan that sounds straight out of science fiction. Mm-hmm. But let's be practical for a moment, right?
Right.
How much is all of this going to cost?
Well, Nemotin estimates a budget of $30 million over 5 years.
$30 million?
Yeah.
That's a lot of money.
It is.
Where are they planning to get that kind of funding?
Well, they're taking a diversified approach.
Okay.
Targeting a mix of government grants, private investments, and even international collaborations.
Okay.
So think of it as like a portfolio approach to fundraising.
Okay.
Spreading the risk and maximizing their chances of success.
Okay, so who are they kind of targeting for funding?
Well, agencies like the U.S. Department of Energy and the National Science Foundation.
Right.
These are agencies that are known for supporting cutting-edge research in energy.
Okay, so those are like the government heavy hitters, right?
Yeah.
But I imagine they're also looking to attract some private investors, folks with deep pockets and a passion for clean energy and maybe,
Absolutely.
some profits. Yeah.
Yeah. In fact, the plan specifically mentions Bill Gates's breakthrough energy ventures.
Okay. So they're going after the venture capital giants.
Yeah.
What about international funding?
Right.
How does that play into this?
Well, the collaboration with Technion opens doors to funding from Israeli sources.
Okay.
Like the Israel Innovation Authority.
Okay.
And plus, you always have those international programs like Horizon Europe.
Right.
Which supports, collaborative research projects across the European Union.
Okay, so they're tapping into like a global network of funding opportunities, right?
Exactly, yeah.
They're leveraging those international partnerships to maximize their chances of securing those like vital resources.
Yeah.
But let's be realistic. I mean, this is a huge undertaking.
Yeah.
A lot of unknowns, a lot of potential for setbacks.
Right. You're right. It's a high risk, high reward endeavor.
Yeah.
There are no guarantees of success and setbacks are inevitable.
Yeah.
But, that's the nature of scientific breakthroughs, right?
Yes.
You have to be willing to push boundaries, to challenge conventional wisdom.
So it's like climbing Mount Everest. Right.
Yeah.
A daunting challenge. Fraught with danger.
Right.
But with the potential for a truly breathtaking view from the summit.
Exactly. And, even if they don't reach the summit,
right,
the knowledge and technologies that they develop along the way could have far-reaching impacts. It's not just about, achieving that ultimate goal of commercially viable fusion power.
Right.
It's about the journey itself, the discoveries and innovations that emerge from pushing the limits of what's possible.
Okay, you convince me.
Uh-huh.
This DCT project is about more than just like clean energy, right?
Yeah.
It's about pushing the boundaries of human ingenuity and inspiring, a new generation of scientists and engineers.
Exactly.
But let's shift gears for a moment and talk about the bigger picture.
Yeah.
What are the potential implications of DCT, not just for the energy sector, but like for society as a whole?
Right.
If this technology like takes off, how could it change the world as we know it?
That's a great question.
Yeah.
And one that deserves a deep dive of its own.
Okay.
And we'll explore those broader implications in the final part of our conversation.
All right, I'm on the edge of my seat. This DCT saga is getting more and more intriguing.
Yeah. It's it's easy to get kind of lost in the gee whiz factor of these futuristic technologies.
Yeah.
But the true brilliance, I think, of Nay Moten's plan is its practicality.
Okay.
He doesn't just toss out wild ideas. He meticulously lays out the research and development phases, outlining clear objectives, deliverables, even potential funding sources,
Yeah.
He's approaching this like a seasoned entrepreneur.
Right.
Which I think is exactly what's needed for a project of this magnitude.
So it's not just a science project.
Yeah.
It's like a full-blown business plan.
Yeah.
Complete with market analysis and like a go-to-market strategy.
Precisely.
Yeah.
He's laid out a 5-year roadmap with a total budget of $30 million.
Okay.
Divided into 3 distinct phases.
All right, let's break down these phases.
Okay.
What's first on the agenda?
So the initial phase, it's all about proving the concept.
Okay.
Establishing a solid foundation for everything that follows.
Okay.
Think feasibility studies, computational modeling, and pushing those exotic materials we talked about to their limits.
Okay, so like a lot of number crunching, simulations, lab experiments.
Exactly.
To make sure this isn't just a pipe dream.
Right. They'll be running simulations to see how HLEC and TPV systems perform under the extreme conditions of a fusion reactor.
Yeah.
And they'll be putting those candidate materials through the ringer, blasting them with heat and radiation to see how they hold up.
Yeah, I imagine those tests are going to be like pretty intense, trying to like replicate that hellish environment inside a fusion reactor.
You're not kidding.
Yeah.
But that's the only way to know for sure if these technologies can withstand the pressure.
Yeah.
Both literally and figuratively.
Right.
This phase is about identifying any potential deal breakers.
Okay.
Early on.
So it's like a rigorous audition process for the materials and the designs.
Yeah.
Like only the strongest survive.
Exactly.
What happens if they make it through that gauntlet?
Okay.
What's next?
Then things get really exciting.
Okay.
Phase 2 shifts from theory to practice.
Okay.
With a heavy emphasis on building and testing a lab scale prototype.
So no more computer models.
Right.
Time to build like a mini version of the real deal.
Exactly.
Yeah.
This is where those specialized teams come in. The optical engineers, the material scientists, the electrical engineers, all working together to create a working model of a DCT system that can handle fusion relevant conditions.
Okay. So they'll be building custom test beds that can generate like those scorching temperatures.
Yeah.
Testing those radiation hardened PV arrays, figuring out how to integrate those like complex cooling and photon recycling systems.
Precisely.
Yeah.
And this prototype, it's not just about proving that DCT can work.
Right.
It's also about fine-tuning the design.
Okay.
Figuring out the best configurations for maximum efficiency and reliability.
Yeah.
They'll be experimenting with the different materials.
Right.
Tweaking designs, pushing the limits of what's possible.
Right.
It's a crucial stepping stone.
Okay.
Towards scaling up to those megawatt level power plants that we talked about earlier.
Okay, that makes sense.
You
need to make sure the miniature version works flawlessly before even thinking about building something on an industrial scale.
Right.
But let's say they succeed.
Okay.
Right? Mm-hmm. They build a working prototype that doesn't like melt down or explode.
Right.
What happens in that final phase?
So the final phase is all about bringing things down to earth.
Okay.
Literally, it focuses on integrating this amazing technology into a real world fusion power plant.
So from the lab to like a full-blown power plant.
Exactly.
That's a huge leap.
It is, yeah.
What does that involve?
It means running large-scale simulations.
Okay.
Modeling how the DCT system would interact with the complex systems of a fusion reactor.
Okay.
They'll be looking at heat transfer, energy conversion efficiency, and making sure it can handle the unique geometry and operational demands of a fusion power plant. They'll be working closely with fusion reactor engineers to ensure seamless integration.
So no more lab coats and safety goggles.
Right.
Time to put on like hard hats and steel-toed boots.
Yes. You got it. Yeah. This phase is also about planning for the future.
Okay.
Laying the groundwork for commercialization.
Okay, so thinking about like manufacturing, deployment, maintenance, all those like practical considerations that come with bringing like a revolutionary technology to market.
Exactly. They'll be developing technical documentation, outlining safety protocols, exploring potential partnerships with industry players.
Okay.
It's about transitioning from a purely scientific endeavor to a viable commercial product.
Right.
You know?
That's a lot to tackle.
It is.
They've got the phases mapped out.
Yeah.
They've got, the research teams assembled a mountain of work ahead of them.
Yeah.
But as you mentioned earlier, there's also the small matter of securing that $30 million to make all of this happen.
Yeah. And that's where Nate Moten's business savvy comes in.
Right.
He's not just relying on a single funding source.
Yeah.
He's targeting a mix of government grants, private investments, and international collaborations.
Right.
It's a smart strategy to spread the risk.
Right.
And maximize their chances of success.
Okay, so who's on their list of potential funders?
So they're looking at agencies like the U.S. Department of Energy, the National Science Foundation, which are, known for supporting cutting-edge energy research.
Okay, so those are the big government players.
Yeah.
But I imagine they're also courting some private investors, folks with deep pockets and a thirst for clean energy profits.
Absolutely.
Yeah.
In fact, the plan specifically mentions Bill Gates's Breakthrough Energy Ventures,
which has a track record of investing in game-changing energy technology.
Yes, so they're going after like the heavy hitters in the venture capital world.
Yeah.
What about international funding?
Right.
How does that fit into the picture?
So the collaboration with Technion opens doors to funding from Israeli sources. Right. Like the Israel Innovation Authority.
Okay.
And, and there's always international programs like Horizon Europe.
Right.
Which supports collaborative research projects across the European Union.
Okay, so they're casting a wide net, right?
Yeah.
They're tapping into like a global network of funding opportunities to make this vision a reality. But let's be honest, even with the best plan, the smartest people.
Right.
This is still like a long shot, right?
You're right. It's a high risk, high reward endeavor.
Yeah.
There are no guarantees of success.
And setbacks are inevitable.
Right. Yeah.
But that's the nature of scientific breakthroughs.
Yes.
You have to be willing to push boundaries to challenge conventional wisdom.
It's like climbing Mount Everest, right?
Yeah.
It's a daunting challenge.
It is.
Fraught with danger.
Right.
But with the potential for a truly breathtaking view from the summit. And
even if they don't reach the summit, the knowledge and technologies they develop along the way could have far-reaching impacts. It's not just about achieving that ultimate goal of commercially viable fusion power. Yeah. It's about the journey itself. Right. The discoveries and innovations that emerge from pushing the limits of what's possible.
Okay, you convince me. Mm-hmm. This DCT project is about more than just like clean energy.
Yeah.
It's about pushing the boundaries of human ingenuity and inspiring, a new generation of scientists and engineers.
Right.
But let's shift gears for a moment.
Okay.
And talk about the bigger picture.
Yeah.
What are the potential implications of DCT, not just for the energy sector, but like for society as a whole?
Right.
If this technology like takes off, How could it change the world as we know it?
That's a great question.
Yeah.
And one that deserves a deep dive of its own.
Right.
And we'll explore those broader implications in the final part of our conversation.
All right, I'm on the edge of my seat.
Yeah.
This DCT saga is getting more and more intriguing.
It is.
Okay, so we're back for the final part of our deep dive into direct conversion technology, DCT. Mm-hmm. We've covered the basics, the challenges, the research roadmap, even the funding strategy.
Right.
But now I'm really curious about, the big picture. How could DCT change the game, not just for energy production, but like other industries as well?
That's the exciting part.
Yeah.
This ability to efficiently convert heat directly into electricity opens up a whole new world of possibilities.
Okay.
Think about areas where we rely on, bulky, inefficient or energy-intensive processes that involve heat.
Okay, that's a pretty broad range.
Yeah.
Right? So we're talking industrial manufacturing, transportation, maybe even things that I haven't even thought of yet.
Exactly. The potential applications are so diverse that it's hard to even grasp the full scope of what DCT could enable.
All right, let's try to narrow it down a little bit.
Okay.
What are some concrete examples where DCT could really make a difference?
Well, one area that immediately jumps out is industrial processes that generate a lot of waste heat. Think steel mills, chemical plants, even those massive data centers.
Right.
All producing, enormous amounts of heat.
Yeah.
That's currently just being vented into the atmosphere.
So we're talking about capturing that wasted heat.
Yeah.
And turning it into electricity. Exactly. Essentially getting free energy from a process that was previously just polluting.
Precisely.
Yeah.
And with DCT, you could do this on a much smaller scale.
Right.
And with much higher efficiency than traditional waste heat recovery systems.
So that would be a huge win for both the environment and the bottom line of these industries.
Absolutely.
Yeah.
But it's not just about capturing waste heat.
Right.
DCT could also enable entirely new manufacturing processes that rely on, very precise localized heating.
Okay, I need a visual here. Give me an example.
Okay, so imagine a 3D printer that uses DCT to precisely heat and fuse materials at the nanoscale, allowing the creation of objects with incredible precision and complexity.
So we're talking about building things from the bottom up, atom by atom, using heat as the tool.
Exactly.
That's crazy.
And because DCT is so efficient, you could do this without needing massive amounts of energy or generating a lot of excess heat.
So that could completely revolutionize manufacturing.
Yeah.
Leading to everything from, lighter, stronger materials for airplanes to custom designed medical implants tailored to an individual's body.
The possibilities are pretty mind-blowing. And we haven't even touched on transportation yet.
Okay.
DCT could have a huge impact on how we move people and goods around the world.
Now you're talking. We're talking about electric cars with DCT-powered engines.
Well, that's certainly a possibility.
Right.
Especially for things like, long-haul trucking, where battery weight and range are big hurdles.
Right, yeah.
But DCT could also revolutionize air travel.
Okay, now I'm really intrigued. How would DCT change airplanes as we know them?
Well, imagine an aircraft engine that uses DCT to convert heat from combustion directly into electricity.
Yeah.
And this electricity then powers electric motors that turn the propellers or fans.
So instead of those big noisy jet engines, we'd have quieter, more fuel efficient aircraft powered by electricity.
Exactly.
Whoa.
And because DCT systems are inherently more compact and lightweight than traditional engines, we could potentially design entirely new types of aircraft. Maybe even personal flying vehicles that are safe, affordable, and environmentally friendly.
Now that would be a game changer. Imagine commuting to work in your own personal flying car.
Yeah.
All powered by clean energy.
Yeah.
I mean, count me in.
It might sound like science fiction, but with DCT, it could actually become a reality.
Right.
But the implications go far beyond just transportation.
Right.
DCT could even revolutionize space exploration.
Well, hold on. Space travel is already, like, incredibly difficult.
Yeah.
And expensive.
Yeah.
How would DCT make a difference out there?
Well, think about the challenges of generating power in space.
Okay.
Solar panels are great.
Yeah.
But only when you're in direct sunlight.
Right.
Nuclear reactors are powerful,
Yeah.
but heavy
Right.
and risky.
Yeah.
DCT offers a potential solution.
Okay. I'm all ears. What kind of solution are we talking about?
So imagine a spacecraft powered by a compact fusion reactor.
Okay.
And this reactor uses DCT to convert the heat from the fusion reaction directly into electricity.
Whoa.
Providing a continuous and reliable power source for long duration missions.
That would be huge for space exploration.
Yeah.
We could finally, like, venture out to the outer solar system and beyond without being limited by energy concerns.
Exactly.
Wow.
And because DCT is so efficient, we could even use the waste heat from the reactor for things like growing food, generating oxygen, creating a livable environment inside the spacecraft.
So we're talking about creating, like, self-sustaining spaceships.
Yeah.
That could travel to other planets.
Yeah.
And maybe even establish, like, permanent settlements.
It's a bold vision,
Right.
but DCT could make it possible.
That's incredible.
And the potential applications go even further.
Okay.
We could use DCT to unlock new forms of communication.
Okay.
And information processing.
Okay. Now you've lost me. How does heat conversion connect to things like communication and computers?
Well, remember those photonic crystals we talked about earlier?
Yeah.
They're not just good at directing light. They can also manipulate light at the nanoscale.
Yeah.
Creating optical circuits that can process information at incredibly high speeds.
So instead of electrons flowing through wires, we'd be using photons traveling through these, like, tiny optical circuits, all powered by DCT.
Exactly.
And because photons travel at the speed of light, these optical computers could be, like, way faster than our current silicon-based computers.
That's right.
That would revolutionize everything.
Yeah.
Computing, artificial intelligence, scientific research. We're talking about solving problems that seem impossible today.
Yeah.
Unlocking, like, incredible discoveries and even creating, like, entirely new forms of art and entertainment.
It's truly mind-boggling.
It is.
And we've barely scratched the surface.
Right.
As we explore DCT further, we're bound to discover even more amazing applications.
Right.
Some of which we can't even imagine yet.
Yeah.
You know?
I'm completely convinced DCT is, like, the ultimate Swiss Army knife of the future.
It is.
But let's take a step back.
Okay.
And think about, the bigger picture here.
Yeah.
If DCT lives up to its promise.
Right.
What kind of world will we be living in?
That's the big question, isn't it?
Yeah.
It's impossible to predict the future with certainty.
Right.
But I think it's safe to say that DCT has the potential to create a world that's cleaner, more sustainable, and more prosperous.
A world where energy is abundant and affordable.
Yeah.
Where pollution is a distant memory. And where technology helps us solve our biggest challenges and explore, like, the vast universe.
Exactly.
Wow.
But it's important to remember that technology is a tool.
Right.
It can be used for good or for bad.
Right.
The choices we make today will determine how DCT shapes our future.
So it's not just about, like, developing the technology.
Yeah.
It's about making sure it's used responsibly and for the benefit of, like, all humankind.
I think that's the perfect way to sum it up.
All right. Well, that brings us to the end of our deep dive into direct conversion technology.
Yeah.
We've covered a lot of ground, the science, the challenges, the possibilities, the ethical considerations. It's clear that DCT has the potential to revolutionize our world in some really profound ways.
It does.
The future is still being written, and it's up to all of us to shape that future responsibly.
Yeah.
And ensure that this incredible technology benefits everyone.
It's been an incredible journey exploring this with you.
Well, thanks for joining us on this deep dive into DCT.
Yeah.
Until next time, keep those imaginations firing, and who knows, maybe you'll be the ones pushing the boundaries of this incredible technology and shaping the future of our world.